we go. Recording has started. So welcome to Friday. Here's the agenda I showed you guys yesterday. We're right. Oh no, that's honors. There you go. AP. This is you guys. So here's our agenda. We are on this day right here. So we're gonna do. Actually, it's kind of time to do a couple of college physics puzzles. So we do that. Now, one of the weird days coming up is Tuesday, so I'll probably be back by 5th period, should be, but well, just for the video for my first two classes, we're gonna have that relocation. In general, you might be relocated in some of your other classes, so here's the full list. If you can see that on video and make sense of that, so there you go. Hopefully your teacher's telling you that anyway. But let's hop into some physics puzzles. So we've got, okay, I'm going to go over two problems today. And these you have to think pretty deeply on. So, all right, so you guys got your thinking caps on, ready to go? Okay. We're going to start with number 23. Yeah, all we're doing today is number 23 and 38. That's it. That's our whole goal today. A girl of this given mass is standing on a plank of this mass. Okay, so girl on a plank. Okay. The plank originally at rest is free to slide on a frozen lake, which is a flat, frictionless surface. You know what? You guys already sort of have a mental model for this. You guys remember that Magic School Bus animation? Right? Wanda throws the ball forward and she gets kicked backward. Right? That actually sounds a lot like this, sort of, doesn't it? Because if you got girl with some mass, you got, well, instead of a plank, it was a baseball. But it was, and they did all start at rest, and they were on a frictionless surface, right? One kicks one way, one kicks back the other way. The girl begins to walk along the plank at constant velocity of so many meters per second at the right relative to the plank, right? Now, as she's moving to the right, what's that plank going to do? Is it going to stay in place? Going to move back to the left, isn't it? Right. Right. So, these questions: what is her velocity relative to the ice? Right? Because this walking speed, let's say that's just her natural walking speed, right? If she's on a moving platform, well, now there's her speed relative to the plank, which actually is what that would represent. And then there's also the plank relative to the outside world, which is question B, what's the velocity of the plank relative to the outside surface? Right? And then what's her speed relative to the outside world, or her velocity? Right, so we actually have 3 different velocities going on. Draw a picture and solve this thing. Right, 23. Right. And I will let you guys know ahead of time going into this. This is probably harder than any question that AP is going to ask you, but I'll tell you at the end, probably the question that AP would ask if they threw you this type scenario too. So let's go through this. Right, we got this big old icy surface. Right, frictionless ice. There's this plank that has some mass. Let's say mass plank. I'll say sub P for plank. Right, is right, I'm going to make up my own number a little bit different from the book. I'll just call it an even 100 kilograms. Right. And then you got mass of the girl, of the M sub G for mass of the girl. Okay. I'm going to round down a little bit from the book, but I'll just call her even 40 kilograms. Something like that, right? Okay. All right, so then she starts walking off to the right. Right. Now, you have to be careful with the subscripts here, because remember there are like 3 velocities we've got to keep track of. Right? And this is one of them. Velocity of girl relative to the plank. Right? Like her natural walking speed. Right? And let's call that, I'll call it an even 2 meters per second. Right? Whatever that walking speed. Okay? So just like normal, my number's a little bit different than the book numbers, but not too far off. 2 meters per second. That's walking. Okay. So this is going to be a conservation of momentum question. Okay. Now, how much momentum do they start off with at the beginning before she starts walking? Yeah, there's 0 momentum in the system. Right? So the sum of momentum before she starts walking is equal to the sum of momentum at any time, right? Because frictionless surface, right? Which is going to be 0 kilogram meter per second, right? So that's going to be mass of the girl times velocity of girl relative to the ice, right? Plus mass of the plank times the velocity of the plank relative to the ice. Right? All right, so all three velocities that we could care about are written somewhere up on this page. Okay? So we got the girl's natural walking speed, which is only relative to the plank because that's what she's pushing against. Right? So that's a given value. Okay? But then from our third person point of view, maybe we're just sitting over on the grassy knoll, like pointing a radar gun at her. Right? If we're pointing a radar gun at her, right, what is her speed? What is her velocity relative to us? What number is showing up on the radar gun? And it's not 2 meters per second. Is it going to be faster or slower than 2 meters per second? It will be slower. Yeah, you're right. Right, and that's that's represented right here. The girl relative to the ice. That's also the number that's going to show up on the radar gun reading. Right, because that platform is getting kicked backward, and that's sort of what's slowing her down relative to the outside world. Right? That's also an unknown value, but that's the other question we got to figure out is, well, how fast is the plank actually moving relative to the ice? Okay, is that okay so far? And there are these 3 different velocities going around, and we know one of them. And somehow we're supposed to figure out the other 2? Huh. Okay. Well, let's do this substitution. Okay, so you guys remember doing like vectors tip to tail, that whole thing? Okay. So we're going to do a sort of a vector addition, but just in one dimension. Let's relate these 3 boxed velocity values. There's the velocity of the girl to the ice, okay, but that's equal to velocity of girl relative to the plank plus velocity of the plank relative to the ice. Right? Whatever the girl's doing relative to the plank, and we know that number, it's just rocket speed, plus the plank motion relative to the ice, that will give us what she's doing relative to the ice, or relative to the outside world in general. Okay? Right, so this expression right here, dash outline this thing. Right? We're going to use in a substitution. I mean, you guys see the big picture formatted. This is sort of like a system of equations, right? I mean, if you just had this conservation momentum, well, there would be 2 unknowns. You can't solve that by itself. But if you can relate these velocities to each other, you can set up this other equation. And you can sub this into girl relative to the ice, this right here. I'm going to sub that right there. Right there. Right? So this whole expression, right? Yes, yeah? All right, so next line, I clean this up a bit. 0 kilogram meter per second is equal to mass of the girl times, okay, now here's the substituted expression right here. Girl to plank plus plank to ice, because that would collectively represent the girl relative to the ice, right? So that total momentum plus mass of the plank times velocity of the plank to ice, okay, has to zero out because there was only ever there were only ever 0 units of momentum in the system to begin with, right? So this mv plus this mv. Okay. Oh, I forgot to. Okay. You guys do see that one of these terms is going to be positive and the other is going to be negative, right? Positive, negative. Right? That makes sense, right? The plug's getting kicked back the other way. Let's start plugging some numbers in because notice this too. Right? Velocity of plank to ice shows up there and also there. Right? And the girl to plank, that was a given value, so that's a known value. You see we're about to get one equation with one unknown, sort of like solve for the unknown variable. Okay? Do some algebra. And so 0 kilogram meter per second is equal to mass of the girl was 40 kg. Right? Girl to plank was your even 2.0 meters per second. Okay. Now plank to ice, we don't know. Plank to ice. Okay. But it shows up a couple of places. So, mass of the plank, we know this number too. This is 100 kilograms. So 100 kg, 100 kilograms. right? And your book value is a little bit different, right? Times the Planck to ice. Okay. Yes, good? Okay, so if you can get that far, then you've actually cracked the tough part, the tough physics, right? Because the rest is just going to be algebra, right? I mean, once you get this far, okay, well, I can solve this. It's just algebra. Okay. So I'm going to distribute this 40 kilograms. Right. So I'll have 0 kilogram meter per second. That's the total momentum in the system that there ever was, because momentum is conserved. That's sort of the principle behind it. Is equal to 80 kilogram meter per second plus 40 kilograms times the velocity Planck to ice plus 100 kilograms velocity Planck to ice. Right? Solving for this variable. Oh, I see like 3 terms on this side. I got 80 units of momentum plus, hey, 40V plus 100V. If you have 40 something plus 100 something, can I just tag these two together? Okay. So 0 kg meter per second is equal to 80 kilogram meter per second plus 140 kilograms times velocity Planck to ice. So subtract over 80 units of momentum, divide by 140 kilograms. Velocity Planck to ice is equal to, well, negative 80 kilogram meter per second, all divided by 140 kilograms. That's going to be negative 0.57 meters per second. Okay. That's the Planck relative to the ice. Then, in physics, whenever you get a final answer, a good thing to do is to check and say, does this make sense? Does this look plausible based on what I was originally given? Okay. So notice that she and the Planck have kind of comparable masses, although Planck's a lot more massive. Okay? She's walking 2 meters per second to the right. Well, the Planck better have a negative velocity, and maybe a good fraction of 2 meters per second. Oh, yeah, that definitely looks in line with, that's something I could believe that number, right? That looks about right. Right, so I think that was actually question B. We actually answered question B first, just based on the algebra setup. Okay. Question A was, what is the last thing we don't know? What is her velocity relative to the ice? Her velocity relative to the ice. Right? So question A, right? And all we have to do is just go back to this. You guys remember the substitution expression from before? Because we've known Grohl to Planck the whole time that number was given. Okay? We just figured out this one, the Planck to ice. So all we have to do is tag these two together. Boink, boink. You get that? Okay? So go back to that. You guys remember velocity of Grohl to Grohl to ice is equal to velocity Grohl to Planck plus velocity Planck to ice, right? Vector addition. Right? Grohl to Planck was given as 2 meters per second. I should have done this. I should have given you guys to the hundreds place. Okay. Let me pretend I did that. Just retroactively give you guys another digit. Plus Planck to ice, negative 0.57 meters per second. Right. So that would be 2 plus negative 0.57. Right. I'm looking at 1.43 meters per second. So yeah, she's still moving forward in the forward direction, the way she's intended to go. That makes sense too, right? But not as fast as if the Planck had been fixed into the ground. Right? Because if the Planck had been fixed into the ground, it should be going 2 meters per second, but she's going a little bit slower than that. That makes sense, right? Okay, guys good there? All right, so a few other things I want to mention about this. One is, if you think about the analogy of remember Maverick Schoolbus wanted to throw the baseball forward. She got kicked backwards. Right? And we sort of solved a simplified version of this. Well, not exactly. Before, say if you knew the speed of the baseball relative to the ground, could you figure out like the pitcher's speed moving back toward second base? Right? If you knew their masses and the speed of the baseball. Right? Suppose that baseball on the radar gun was showing up as like 30 meters per second, something like that. Okay. That means that she could actually throw that baseball faster or slower than 30 meters per second if she'd been fixed into the ground. Yeah, a little bit faster, right? Maybe, well, it depends on the masses, right? But a little bit faster. So same story here. Right? This girl can walk pretty fast, but the radar gun reading is showing up a little slower. Okay. Another thing I want to mention about this is there is number 24, the very next question in the textbook, okay, is exactly the same scenario, except without any numbers. They say, can you solve this in terms of variables? So if you want a real fun, challenging question, then solve in terms of variables. Okay. And the last thing I want to mention about this problem goes back to something I mentioned before, that this is almost certainly harder than anything AP would give you. Maybe one of the very difficult FRQs, possibly. But what AP probably would ask, maybe as a multiple choice question, if you saw like this exact scenario, what would AP ask? AP likes to ask questions about center of mass. So say the center of mass between her and the plane. Okay. So suppose it all starts stationary, it all starts at rest. Right? See if you guys can figure this out. So here's an AP question. If she's walking forward and the plane is getting kicked backward, right? Where do you guys think the center of mass is moving? To the right, to the left, or is it staying stationary? Stationary. Yeah. In fact, if you only focused on that center mass, you would never know when she started walking or how fast she was walking. You would have no idea, right? How about this? What if she jumps off and starts sliding to the right and that plane is sliding to the left? What would happen to the center mass? Does it still just stay stationary? Yep. You would never know when she jumped off. What if you put that in reverse? What if the plane is sliding to the right and she's doing a running jump to the left, she jumps on that thing. And the whole time you're only focused on the center mass between those two objects. Right? Maybe it was stationary the whole time, maybe it was moving the whole time. But regardless of either of the situations, would you ever know when she landed on that plane? Just focusing on center mass, you would never know. Right? So the only way that would ever change is if there was an outside force acting on the system. The reason this works out is because this is a closed system. Right? It's just a closed system, just her and the plane. Right? There's no outside forces. Well, except for the gravity and the normal force, but those cancel out anyway. Right? You can treat it as a closed system. Okay. Next one. Good one we're doing today. Number 38. Two shuffleboard discs, equal mass. Check where we are here. We got this. Right. Two shuffleboard discs, equal mass. One orange and one green. I'm gonna switch those colors to red and green because I have, well, I don't have an orange pen, but I have a red pen. So put some colors on here. Right. We'll call them red and green. Involved in a perfectly elastic glancing collision. Right. The green disc is initially at rest, and it's struck by the red disc that's moving to the right at so many meters per second. Okay. After the collision, the orange disc moves at, the red disc moves at 37 degrees up from the horizontal axis, and the green disc moves 53 degrees down from the horizontal axis. Okay. Determine the speed of each disc after the collision. Okay. So, hey, this looks like it's going to be a conservation of momentum because there's a collision involved. Okay. It's in 2 dimensions. The only other 2-dimensional one we looked at already is this one right here, number 18 from yesterday. You guys remember Boing bouncing off the wall? Right. This one's going to be a bit more involved, but it is a 2-dimensional conservation of momentum question. So momentum has to be conserved in both the x direction and also the y direction. Okay. Hey, speaking of the y direction, let's get some thoughts before I start throwing numbers down on paper. Okay. What is the total momentum along this y-axis? If one disc just started at rest and the other was moving horizontally, what's the total y-direction momentum? Yeah, 0, right? So do you think after they boing, collide off each other, and one goes kind of upish and one goes kind of downish, do you think that the up and down have to cancel out? Right. Let's start putting the picture together. Number 38. So get those axes going on. Got an x-axis and a y-axis. Right, we got this. Now, they never did tell you what the mass of these things were. All I said was that the masses were equal. So I bet the mass would cancel out at some point to figure out the speeds. Right? Think ahead. Tell me if that's kind of confusing though. Oh, let's say the collider here. Bam. Right. If that's kind of confusing, remember if something works in general for any mass, like as a variable, then it better work for every single specific situation, including if you just made up a number like 1 kilogram. So if you need to, just call them like 1 kilogram each. You can plug that into equations and do it that way. Okay. If you pay real close attention, you may have noticed that these are actually at right angles to each other. Okay. I'm going to make this one really short, and you might see why already, and if you don't, then you'll see in a minute. Okay. This is a 37-degree angle. This is a 53-degree angle. Guess what's 37 plus 53 degrees? Yeah, you guys see it? Well, okay, I didn't draw that exactly right, but this should be a 90-degree angle, shouldn't it? Something like that. Oh, another thing. You guys have seen these angles before. These angles pertain to a what triangle? 3, 4, 5. Yeah, 3, 4, 5 triangles have these angles, don't they? Huh. I wonder if there's going to be some 3, 4, 5 geometry going on here. Okay, let's call this guy the red one, which boing bounces that way. Okay. And then the green guy, like right here. Okay. So red and green. Okay. All right, well, we're dealing with vector values, right? Like velocities, momentum values. Those are vector values. So let's break these into components. Do some analysis. What's going on vertically versus horizontally. Okay. So the green one is a little bit to the right and a good amount down. Okay. And the red one is going like really fast to the right. Okay. And a little bit up. Yeah. Okay, is that right? Now, I knew ahead of time to make the green one going kind of slow compared to the red one. Suppose these are, I can interpret these as momentum vectors or velocity vectors. I'll do them as velocity vectors and then solve it that way. Okay. So I'll call this velocity, red, final meaning post-collision. We're going to solve for that. And I'll call this guy velocity, green, final meaning post-collision. Right? Okay. Got to figure out those speeds, those velocities. Okay. How did I know to make the red one going really fast and the green one kind of slow? Right, so look at the magnitudes, right? How did I know that? Right? And I knew that based on the y components, right? You guys see how fast this one's going strictly up? How fast this one's going strictly down? Right? So, those are exactly going to cancel out, aren't they? Like that? Let's get these component values. So I know this is going to be V red final times what? V red final times sine of 37 degrees. Right? This is going to be V green final times sine of 53 degrees. Okay. This is also the horizontal components. Let you guys imagine those because I'm kind of running out of paper space there. Okay. So what's our equations? Okay. So this is something to do with momentum. Sum of momentum in the x direction before the collision must equal sum of momentum in the x direction after the collision. Okay. Sum of momentum in the y direction initial equals sum of momentum in the y direction final, okay, which is also 0 kilogram meter per second. Okay. This right here is your system. Right? That's what's going to let you set up this whole thing and solve it. Right? Is that right? Okay. Right. Got a little space down here, so let's turn these into equations. Okay. Momentum is mass times velocity, so whatever this mass m is times, oh, I forgot to label initial velocity. Okay. I'm going to double the book value. I'll call this 10 meters per second. Okay. I think your book said 5, I'm doing 10. But I do like the fact that it's a factor of 5 because you guys remember the whole geometry about 3, 4, 5 right triangles? Do you think they picked those angles so that the numbers are going to work out really nice in the end? I bet they did. Let's see if they do. So times the original 10 meters per second. Okay. That has to be conserved. So it's going to be mass. This red mass, which is just mass, right? Times V red final cosine 37 degrees plus mass of the green one, which is again just mass, times V green final times cosine 53 degrees. Okay. Now the cosine components I did not label up here, but you guys see what those would be, right? Just these two right here. These two added up have to equal the initial momentum. You guys see where I got that from? Who's got questions so far? Okay. So that's this setup. Okay. Now how about the second line? Okay, so that guy right there is this guy right here. Okay. This guy right here is going to be there was only ever 0 kilogram meter per second vertically along the y-axis. Okay. That's going to go to mass times V red final sine of 37 degrees. I would say this plus this, but looking at the geometry, I mean, these angles are heading opposite directions, right? One's going clockwise, one's counterclockwise. One tries to, I need a negative sign somewhere. So basically this minus this, better zero out. Okay. Mass of the green one, which again is mass. Okay. Velocity green final times sine of 53 degrees. Okay. Here's my system. Okay. System right there. Okay. Good so far? Now, if you can do that setup, then we're pretty good on the physics front. Right? Actually, we're pretty much done with the physics. The rest is just going to be, how well do you know algebra? So, you know what, let's do a little cancellation right here. Okay? You guys see a bunch of terms that all have a what in them? M. So let's just go ahead and bump that. Doink, 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 doink. That's the sound of M canceling. So 10 meters per second has to be, okay, now we don't know what velocity red final is, but hey, cosine of 37 degrees. What is cosine of 37 degrees? Huh, you guys see it's basically 0.8. Okay. I'm going to call it 4/5. Okay, is that okay? Just as a fraction? Okay. Don't have to do that, but it's going to make this a little bit easier to solve. Velocity green final times, okay, what is cosine of 53 degrees? Oh, that's 3/5. Okay, sure. Right, and then 0 meters per second, if you cancel out the m. Okay. Velocity red final times, what is sine of 37 degrees? That's 3/5. Plus, oh, oops, no, minus, right, minus. Just gotta take care of that negative sign. Velocity green final times, what is sine of 53 degrees? 4/5. Okay. Okay. Hey, couldn't we just get rid of all the fractions by multiplying each of these equations by what? 5, right? Okay. That's one reason I did the fractions. Okay. Is if you just multiply everything by 5, okay, then everything's still balanced on both sides. Okay. So I got 50 meters per second is equal to 4, well, okay, 4 VRF plus 3 V green final. Okay. F is final, like post-collision. Okay. And then 0 is equal to 3 V red final minus 4 V green final. Okay. Ooh, okay, so now this is a system of equations that yeah, we're working on a little bit. That's some algebra. This looks a lot cleaner. This looks like something you might find in Algebra 1 textbook if you're solving a system of equations. Okay. So you can do substitution. I'm going to do elimination. Okay. I'm going to take this whole bottom equation and multiply it by, look at this trick. You guys see the V green final? There's a positive and a negative one. Okay. If I take this bottom one and multiply it by 3/4, you see that these are going to match. And then if I add these two together, they're going to cancel out. Okay. That's how I can eliminate a variable and figure out this one and go back and figure out the other one later. Okay. I'm going to multiply this whole thing by 3/4. Okay. And then I'm going to add these up. let's do this all in one smooth move. 50 times 3/4 of 0 is 50. Equals, right? What is 4 plus 3/4 of 3? Okay. That is 6.25. And that would be the red post-collision. Okay. And then 3/4 of 4 is 3. This zeroes out. Okay. Right. So just a little math trick right there. Okay. And then divide both sides by 6.25. Would that give you B red final? B red final, say post-collision, is, what is 50 meters per second divided by 6.25? It's exactly 8 meters per second. Ooh, how nice. And the other one, well, could you pick like any of the previous steps we've been doing and figure out what the other guy is? So V green final, like post-collision. Okay. Let's say pick this bracketed equation right here, this very last point, right? So 3 times red final would be 3 times 8 is 24. 3 times 8. Okay. Move this over, divide by 4. It gives me exactly 6 meters per second. Right. Is that a little algebra there? Right. Oh, remember how this thing was originally coming in at 10 meters per second? You got this Boyne collision, and they gave us these 3, 4, 5 associated angles. Okay. Now look at the final answer. It exactly lines up with those ratios. Right? So 6, 8, 10. Is that the same thing as the ratio of 3, 4, 5? Same thing, isn't it? Right? Guys get that? All right. So the important physics thing is breaking these into components and saying after the collision, the momentum along each axis is conserved. Once you have that set up, then all the math falls out of that. Last thing I did want to mention about this one is that they did mention that this is perfectly elastic. But notice that we never really directly used that for solving this. We just did Planck conservation of momentum. It happened to work out. If you go back and you calculate the kinetic energy before and the kinetic energy after, if you want to check this, you can see that the kinetic energy does happen to be conserved. Okay. So here's what I'm thinking, is that even if they never said it's perfectly elastic, and we totally ignored whether it would be or not, right, we would still get the same numbers. Okay. And then if you went back and checked, like, is it elastic or not, you would figure out that it is elastic. Okay. It just happens to be that for equal masses and for these particular angles, the only way that you can have exactly like these angles from this collision is for it to be perfectly elastic. Okay. You guys right there? All right, that is a wrap on